Hello, welcome to expected value and decision making under risk and uncertainty. So here's an overview. We're going to be talking about decision making frameworks under three different scenarios. One, games of chance. Two, stock market investing. And three, war. So what's the difference between risk and uncertainty? This is something that I want to address before I commence with this video. So Frank Knight, 1921, an economist, made an important distinction between risk and uncertainty. Risk he defined as situations where the possible outcomes and their probabilities are known and can be estimated. Rolling dice or flipping a coin, we know the probabilities of what will occur. In uncertainty, he defined as situations where the possible outcomes and their probabilities are both unknown. An example here would be launching a technology product, or even more ominous, entering war. So first, we're going to be discussing some games of chance. And before I begin with that, I'm going to start with the expected value formula. Highly regarded in statistics. It's one of the first things you actually learn in a statistics class. So let's begin with discrete random variable. So we've got possible values of x1 to xn and corresponding probabilities of probability of x is equal to xi. So the expected value would be the summation of all the possible values times the probability, the corresponding probabilities. You could say the same thing for continuous variable, except this time with the summation, it's basically a integral. And instead of the probability, the corresponding probability, it's a probability density, okay? That f of x is a function. So let's start with what a discrete expected value is. It's a defined set of probabilities of events, right? So a dice has 6 outcomes, 1 to 6. Each side of the dice has 1 in 6 chance of occurring. So it follows a uniform distribution where outcomes are equally likely. A coin has 2 possible outcomes, heads and tails, and each side has a 1/2 of a chance of occurring. So you can see by these graphs what it looks like. And basically, it's just equally likely, right? They all have equal probabilities, the dice roll, and same with the coin flip, what I've just said. And they're perfectly calibrated probabilities, right? So that's an important idea because it reflects the outcomes that actually occur. So let's talk about a coin toss and calculating its expected value. So say that you are asked to make a wager. If you flip a coin and get heads, you make 100, otherwise you make 0. So we would do 1/2 times 100 plus 1/2 times 0 is equal to $50 expected value. This is a pure gamble, but it's a positive expected value, and you should take this proposition, right? It's a gamble, but it's perfectly calibrated, right? We know beforehand the exact probabilities, risks, and the exact possible outcomes. A positive expected value would lead the person to take the bet. In this case, what we saw earlier, they should take that proposition. And a negative expected value would lead the person to not take the bet. So how would expected value work in a fair game? We would have half a chance of winning $1 and then half a chance of losing $1. So if we add those two up, it would be expected value of 0. So that would be considered a fair game. So a fair one-to-one payoff on a 50-50 event has the expected value of 0 per $1 bet, no edge either way. So how would expected value work in a casino? So casinos make money by changing payouts or probabilities. So the player's expected value is less than 0. Example, they pay only 95 cents for a $1 win on a win outcome, right? So this is simplified. Casinos use many mechanisms such as this. We saw the roulette wheel. Same probabilities of 0.5 and 0.5, but payoff on win is 0.95, loss is minus $1. So that's their edge. And basically it's gambling, right? If we calculate the EV, we have 0.5 times 0.95, what you would win, and 0.5 times -1, what you would lose. We do some algebra, and we see that the expected value is -0.025. So you would never want to go to a casino and work the roulette wheel at all. It's pure gambling. Now I want to be talking about something called variant perception, and it's used in poker and stock market investing. Variant perceptions means having a different view from the consensus, the crowd, while also being right about it. In a pure gamble with fixed odds, roulette, fair dice, variant perception cannot be applied. Everyone knows the true probability, so there's no room for a unique perception. Your EV is negative or 0, fair game, regardless of your beliefs. So we saw that earlier, that we could make calculations on these gambles because the outcomes are known, regardless of how you feel about it. They're known. So in gambling situations with uncertainty or misperception, and I'm going to include poker, sports betting, horse racing, and stock market investing, variant perception can be applied. These are essentially cases where gambling becomes investing with variant perception. Okay. So in our earlier definition of risk and uncertainty, we saw that uncertainty is something that we don't know the outcomes of, right? Variant perception allows us to apply our unique perception or ideas to outcomes that might be uncertain, right? Um, so that's what I want to say. So in poker, players misestimate opponents' hands ranges. This can be exploited. Sports betting, bookmakers' odds reflect consensus. If you perceive the true probability differently and are correct, you create positive EV. In stock market investing, you have a crowd of participants. The difference between price and value, commonly called edge, comes from having a substantiated view that diverges from what the market reflects. So here's an expected value formula for the continuous variable. We saw that earlier. And in continuous cases, the outcomes are theoretically infinite. Here's a continuous expected value calculation for a normal and a t-distribution with degrees of freedom of 5. You could see that they have similar expected values, but the swing ranges are different, right? It's plus or minus 600 for the normal and plus or minus 1400 for the t. And this is important to know because you want to know you're always like if you're calculating stock market returns, for example, you always want to know or calibrate what you think the returns will look like, right? If you calculate it as a normal, basically you might miss out on the large swings, but you'll also be missing out on the large swings on the opposite side of the direction where you could possibly lose money. Okay, so it's important to kind of have this idea in your mind of what you think the distribution of outcomes will be, right? So here's continuous expected value, the two distributions. This time I do a t distribution with 3 degrees of freedom, but you can see the fatter tails. And you can see that the fatter tails has more density, right? So the likelihood of more extreme outcomes is higher for the red dashed line, right? Now I'm going to be talking about something called reification. So in statistics, reification is the use of an idealized model of a statistical process. This The model is then used to make inferences connecting model results, which imperfectly represent the actual process with experimental observations. So this is basically your machine learning modeling and your statistical modeling, right? There's an element of risk, but there's also an element of uncertainty. I'll show you kind of a decision-making framework regarding what occurs shortly. But here's a simple OLS model, right? And we've got the beta ones, beta twos, beta n's. In machine learning, we call these things features, right? Beta 1, x1, x1, x2, xn as features, right? And how that influences the model. If we had omniscience, right, we could know possibly everything that will affect y, which is the outcome, and we would have perfect predictions, right? But in this model, basically, we leave room for some level of uncertainty, which is the error term. And it accounts for unknown factors influencing the outcome. And we know if we wanted to predict like the stock market or whatever we wanted the target market variable to be, there are things that we just can't know beforehand, right? That's the uncertainty. An example was COVID, right? Like if we were using like these statistical models or machine learning models at the time to predict stock market returns, we would not have accounted for this in our models. But we shouldn't be so hard on ourselves if we devise or create a model that in general predicts well, um, predicts stock market returns well. So I mean, here I'm showing basically what it is, like a decision-making framework that we should follow, right? Obviously, we want to optimize for having a well-calibrated model and a good outcome, and that's skill. That's a box that we can control, whether that be through our research, reading, um, conversing with experts, right? This could help us achieve a good outcome. But there are also times where a well calibrated model will lead to a bad outcome, right? And that's just bad luck. For example, COVID, right? I mean, I don't know what people were saying at the time, but I think they were saying it was like some like around the 200, 300 standard deviation event. It's just outside of people's awareness that something like this could occur. On the other case, you've got poorly calibrated models, right? Models that are basically not good, poorly made up, not well researched, bad theory, bad bad ideas behind the model, right? Like you're just basically picking variables that are correlated, which might not have any like real causation. This could lead to good outcomes I mean, this could lead to good outcomes because of the fact that it's just luck, right? There's some uncertainty built into the model, and that's what it could occur. But then you could also have a bad outcome, and that's just purely your mistake, right? You made the mistake of looking at variables that might not be influential, and you didn't do your research. Now I'm going to be talking about decision-making framework in in the case of war. You're going to see that a lot of uncertainty plays into this, and there's a different framework that we could use to approach decision making. So this is a quote that comes from Leo Tolstoy's War and Peace. Napoleon invaded Russia, and there's a lot of passages in the book that talk about basically how uncertainty kind of plays a role in military outcomes. So he says, what theory and science is possible about a matter, the conditions and circumstances of which are unknown and cannot be defined? No one is able to foresee in what condition our or the enemy's armies will be in a day's time. Sometimes a detachment of 5,000 is worth 30,000, while at times 50,000 run from 8,000. Okay. So this is the uncertainty element of how it's very difficult to calibrate these type of scenarios. And decision making, usually people are not making decisions based on expected value, right? So, from a statistical framework to an actual practical framework, we're trying to bridge that gap. Now, I talked about variant perception before, where I was talking about market edge, but variant perception could also mean, in the case of war, something like where people are seeing different outcomes, right, of a particular situation. So, in our latest news, we've got the Ukraine war, and America is looking for some type of resolution. I mean, this was beforehand. I mean, as more news come in, basically America has been updating its beliefs on how Russia will behave. But basically, there's two different perceptions going on, right? And in this quick, short example, basically the US is thinking, oh, it's 10% war, but Russia is thinking 60%, right? And that could be due to historical information, like the historical relationship between Ukraine and Russia, that America is just not understanding. Okay. So here's the problem that I've been mentioning. We're not given well calibrated probabilities, right? In situations like that, expected value falls apart in real life situations. We never know the true probabilities of a particular outcome. Human psychology influences how we see the probabilities of outcomes. The stock market and war, we cannot rely on an expected value decision approach, which is purely based on mathematical theory. Precise probabilities and outcomes are usually not possible. So we saw that in the stock market. I mean, there is some expected value type of thinking or framework that you could use, but I would say also that you would have to use this idea of variant perception to kind of look at what the uncertainty is, right? We have to stare it in the face and say, what is it that we don't know? We could miscalibrate probability distributions. We could not include variables, which I alluded to earlier, right, with this whole reification idea. So it's important to know exactly what framework you're living in, right, in terms of the environment or the problem you're trying to solve. So here's a guy that comes from, has a blast from the past, Donald Rumsfeld. 1932 to 2021 is how long he lived, was the 13th and 21st US Secretary of Defense, serving two non-consecutive terms under Presidents Gerald Ford and George W. Bush. He was first appointed Secretary of Defense in 1975, serving until 1977 during the Ford administration. He returned to the role in 2001, serving through 2006 under President George W. Bush, during which he played a pivotal role in shaping U.S. military strategy in the post 9/11 era, particularly in the wars in Afghanistan and Iraq. And whatever you might think of him, I mean, people are not fond of him and the George W. Bush administration, but he did leave some type of intellectual framework to make decisions under these types of situations. And it's called Rumsfeld's matrix, right? There's known unknowns, known knowns, known unknowns, unknown knowns, and unknown unknowns, right? So things we are aware of and understand, things we are aware of and do not understand, things we aren't aware of but understand, and things we aren't aware of and don't understand. So that sounds a little bit confusing, but I'll clarify it a little bit more. Known knowns you could look at as facts. Known unknowns is questions, right? So you know about it, but you're asking questions because there's some level of not understanding or uncertainty. And then there's unknown knowns, which is overlooked knowledge, right? So your research is not complete or whatnot. Unknown unknowns is surprises. A philosopher by the name of Nassim Taleb, he's famous for this black swan events, and that would be an unknown, something that just comes from left field. I mentioned COVID earlier. So here's a business example. Known knowns would be a company knows its current sales, revenue, and costs, right? Those are just purely facts. Known unknowns, a startup knows it doesn't know how consumers will react to a new product. So you know your ignorance in this situation. Unknown knowns, a company has customer complaint data sitting in a database, but doesn't analyze it, so the insight remains unknown. So this is purely negligence, right? If you have a lot of data and you're just sitting on it, you've got a lot of information that you could basically work with, but you choose not to, right? So you're not going to be able to reap any insights or benefits from understanding your data. And then unknown unknowns, before 2022, most companies had no idea that ChatGPT and large language models would disrupt customer service, copywriting, programming, and education so quickly. So that's just something that came out of. I mean, it was developing, but I don't think the public understood it. So the public might have seen it as a black swan. Maybe experts might have seen it as something like a unknown known, right? Now I'm going to be talking about the Iraq War, using some of the decision-making framework that Rumsfeld gave us. This is Colin Powell, the guy in the back is George Tenet, who's the former CIA director. But basically, they're at the United Nations trying to make the case for Iraq's WMD. And he makes this statement. Okay, he says, "My second purpose today is to share with you what the United States knows about Iraq's weapons of mass destruction. Iraq's behavior demonstrates that Saddam Hussein and his regime have made no effort to disarm as required by the international community. Indeed, the facts in Iraq's behavior show that Saddam Hussein and his regime are concealing their efforts to produce more weapons of mass destruction. Every statement I make today is backed up by sources, solid sources. These are not assertions. What we're giving you are facts and conclusions based on solid intelligence." So you guys could think about how this fits into Rumsfeld's matrix, right? In this article, this came out March 9th, 2023. 20 years ago in Iraq, ignoring the expert weapon inspectors provided to be a fatal mistake. Okay. And it goes on to say that the ISG found no WMDs in Iraq, and returning to Congress to testify on 28th January 2004, Kay admitted we were almost all wrong. He blamed a human agents inside Iraq in the months before the war, an analyst being under pressure to draw conclusions based on inadequate intelligence. True, the intelligence K and many other Washington, D.C., London, and other capitals had chosen to listen to was inadequate and flawed, but there was plenty more information that they ignored. Okay, much of it coming from many weapons inspectors working um, including inside Iraq, including U.S. nuclear experts under UN mandate for 4 months in 2002 to 2003. So we could kind of refer to this that matrix where basically there were known unknowns, right? There was data that was there, but they didn't look into it, and that was a mistake. Thank you very much. Have a good one.